welcome. Let me welcome Felix Naumann, who is visiting our department and giving this talk that seems to be really interesting, a new dimension of data analytics, not just data analytics, but new stuff. So Felix, for those of you who do not know him, maybe the youngest, because we know everybody working on areas related with the databases knows Felix since some years. Felix did a lot of work on data integration, data quality, and now data analytics, and is a very well-known scientist. He now moved, because I remember him in another university at Humboldt, but now he moved at, let me say, Hasso-Planck University, right? Correct? Hasso-Plattner Institute. That's a private institute, but also related with the big universities in the Berlin area. The point is that even in Germany, you may be annoyed by bureaucracy and decide to move on the private side to eliminate this problem. So in Italy, he is just experimenting some little bureaucracy, like being, for instance, paid. Felix said, I come for free because the procedure is more costly than the money one could get, and so on. So he told us that this institute is really, it's good from a research point of view, and is very easy to be there from the point of view of the internal procedures, right? Okay, so it is really a pleasure to have you here, and please, you may start. It's just streaming, so they cannot ask questions from...
Okay, yeah. So dear streaming audience, you're very welcome to contact me after the talk. Send me an email if you're interested. So Tiziana, thank you very much for inviting me. I did not know how much I could earn here, but I'm very happy just to be invited. And it's my absolute pleasure to be able to give a talk here on one of the research topics that we're pursuing, exploring change, or looking at how data changes. And this moving image that you see here in the background is just a piece of art. It's not a product of what we're doing. It looks a little bit like the Matrix, but it's supposed to signify that everything changes all the time. There's this Greek saying, pantare, everything changes or everything flows, and so does data. And this is what this topic is about. Since you mentioned Hasso-Plattner Institute, I just want to spend 10 seconds about what it is. So Hasso-Plattner is the co-founder of SAP, or I think in Italy you call it SAP. And so he's the German Bill Gates, and is funding this institute, has put hundreds and hundreds of millions into this institute. It's very expensive to run an institute, as your government will also know. Indeed, we do educate students. We have bachelor, master, PhD programs, and function just like any other university. We're affiliated with the University of Potsdam in Germany, right on the border of Berlin. So actually, I can tell you that this here is already Berlin. Anyway, so now to the topic. Let me skip over this slide. This is the project that we call Dianos, and I hope, being in Italy, that you appreciate how we wrote Dianos, because the original URL was taken, so I thought I'll take the Italian way of spelling it, or the Roman way of spelling it. So this is joint work with Tobias, who's in the audience today, Leon, and then from AT&T, Dmitry, and Divesh. Divesh, I'm assuming many of you know as well, and this whole project was an origin of me spending a research stay with AT&T, and a lot came out of this research stay, this whole project. And when I talk about change, one easy way to think about this project is it's the first derivative of data. right? So this is just a logo here. It's not a mathematical equation, but this is what we're worried about. We're thinking of how and when and why does data change. We're not interested in the actual data. We're just interested in the fact that it has changed. When it has changed, where it has changed, who made the change, these kind of issues. That's why I also said it's a new dimension, because at least we believe these things have not been regarded before. So it's not temporal database analytics or so, because we're not looking at time constraints or anything. We're just looking at the change itself, not how does the data change over time. So what do we want to do? For a given dynamic, changeable data set, we want to capture and summarize the changes at instance level and at schema level, and then we believe that we can drive many different interesting applications with knowledge about data change. So a common example that we always use, so what changes a lot? Wikipedia changes a lot, of course, right? Any old database changes a lot, of course, but we don't have good access to that. But Wikipedia is a great example of things changing arbitrarily, editors going in and changing something. And these are patterns that we'd like to look at, right? One fun example is the following, right? So if you go to Wikipedia, into the info box, this box on the side, and check out the name for the city of Chicago in the US, right? So city of Chicago is the most common name for that city, but there are plenty of other names. So if you go to Wikipedia, you can find all sorts of stuff, and some more stuff, and some more stuff. And because I'm in the US, I can also show all this stuff, because in the US, some of these names are, let's say, rather frightening. But you can see other reasonable things like City of Chicago, Illinois, or the City of Chicago, or City of Chicago, Illinois spelled out. So some of this is vandalism, clearly. Some of them is non-knowledge, and some of it is real. And one of the questions we might want to ask, well, what is the correct name of the city, given all this information, right? And so you could ask a question of how long did each of these names stay on the web page? Obviously, for some of them, we hope they were deleted very fast, but others, might sound reasonable and stay up there for quite a long while. So why does data change? Why does it change? Well, first of all, the real world changes, so we hope that that's reflected in the data somehow, right? At another level, we might have conceptual change, so the schemas change, the perspective on our data change, so we want to revise our database or our model, right? A representational change, this might just simply be renaming attributes, for instance, or adding or removing attributes to a table. And then, of course, lots of accidental change. Let's call it vandalism or errors or what have you. So why is this interesting? There are lots of use cases for this. One, the thing that's driving us is just simply curiosity. We want to explore what's going on with our data, right? Sounds kind of interesting, at least to people like me. But you could have lots of very specific applications. You could say, well, can I understand how data is produced? So for instance, if there are ETL processes feeding a data warehouse, right, then you can observe certain patterns of change, and then you can maybe find irregularities in that pattern, right? Or you can discover transactions. This is an application that is interesting for AT&T and probably many companies, where you have some central databases and the administrators no longer have any idea who's actually able to change data in that database. So transactions come to that database and happen, and nobody really knows what's going on anymore because it's an ancient database and many, many people write and read to it and from it, right? I'm not going to go through all of them. Let's see what else we have. So one interesting use case that we've been exploring a little bit is data cleaning, schema cleaning. So here the idea is that I can see some kind of a trajectory of data. So data is moving into some trajectory, so I might know what a true value is. Or I might see, this is a fun project that we had, we're looking at how a table grows. And as it grows, it might reach some certain limit, and then we know it's complete. So at the beginning, a table grows a lot, and then slowly and slowly it keeps filling up, and at some point nothing much happens anymore. Then we can say, we think this table is complete because it's not growing anymore, right? And so we say, this is clean data, it is complete. So these are the kind of things you can do. Here's a visualization of some very initial analysis that we did. So we looked again at Wikipedia info boxes of settlements, right? And we looked at different prominent attributes like area code, coordinates, the image, the name, etc. And here you can just see a heat map of how much what changes. So you can say which attribute changes the most, right? So the name confusingly changes the most for many of the cities, right? You can also see which cities are prone to more change. So you can see the city of Rome, the info box of Rome has many more changes than that of Berlin for some reason. Maybe there are more vandals, maybe the facts about Rome change more often, maybe the population of Rome grows faster, and that's why there are more updates to it. So once you have this kind of data, you might be curious as to why you're observing this change and then dig a little bit deeper, right? And I would say these are kind of questions that nobody's really asked before. I'm not saying this is useful, but for sure it's interesting for now, right? So just to make it clear, I mean, this is kind of a symposium or colloquium, but you're very welcome to also interrupt me for questions. Yes, absolutely. Is the absolute number of changes that we can observe since the existence of Wikipedia. So, okay, very good question. So how do we know this? Yes, so the good thing is that Wikipedia has a history of every single change ever to anything in their data. These are, you can call them versions, but it's actually much more fine-grained. It's really every edit. You go to Wikipedia and fix a typo and say save, we can observe that, right? Yes, yes. Yes, in the info box. Just in the info box for Rome. The name, yes. Well, I just showed you the example for Chicago. You think Italians are more well-behaved than Chicagoans? Yes. Yes, see, this is why this is interesting research, because this stuff goes on. What can I say? I mean, I'm not making this up, right? I mean, you can verify this. Yeah. Yeah, and this is as of, I'm going to say 2018 or 19 or so, so it's more now, right? Yeah, so this is kind of interesting, right? And it's exactly, so you're wondering which processes change this, right? And if you're the owner of a database, let's say you have a master data management system with all your customers, right? This kind of stuff would also be interesting, right? What changes? Do customers move around a lot? Do I find systematic changes that the phone numbers are reformatted? I will be able to observe all these things given the history of the data, right? Let's say the transaction log of the data. I will talk a little bit more about the data sets behind this, so this might be helpful. So this is the agenda. I'm not 100% sure how much time I have, but I'll see how far we get. We might skip a few points at the end. So the first thing is we're going to look at some data sets as promised. We will show, or I will show, how we model this data. We call it a change cube. It's like a data cube, but with a change dimension. And we'll look at some tooling that Tobias actually built. And then we're going to look at some research projects. The first research project is table matching. So if you have many, many tables, let's say in a data lake or so, that change all the time, how do you know which one is a version of which? It's not trivial. You think it's obvious. It's not obvious at all. And I'll show you some reasons why, right? And then one specific project that Tobias in this case is working on is Schema Recommendation. This is what I mentioned earlier. I see lots of schemata change. Maybe some others should change with it, right? So as I observe renamings in a schema, I could say, actually, that's a good renaming. These other schemas should also be renamed, right? And then some role matching. It's a little bit like data matching across time. We'll see what that is. And then, of course, an outlook with some challenges. But again, so Maurizio, thank you. Interrupt me if you do have questions or comments, right? Okay, so this is about the Wikipedia info boxes, just as one data set that we've been using quite a lot, right? So you can download the entire edit history of Wikipedia as of, let's say, 2019 or so. There's 122 gigabytes of dump, basically, right? And then we extract all the info box template revisions, so every time the info box has changed, and then you get 3 gigabytes, and then we do matching of info boxes, because even on one page you might have multiple info boxes, and in the end you calculate the delta, because we don't see the actual changes, we just see the old version and the new version, so you have to figure out what actually changed, and then we have these change records, so 25 gigabytes of change records. So it's also big data. No? We have up to the millisecond temporal information. Yes, yes. Of course, several changes could be lumped into one, right? If you open a table and change a little bit and hit save, you have multiple changes in that one instance, basically, right? But yes, it's very fine-grained. actually what we do, I mean, I can tell you already now, is so, especially on Wikipedia, you do have vandalism, right? So I think like 10% of all changes on Wikipedia are vandalistic changes, right? But these are often reverted a second or two later. Either an editor notices it, or it's clearly recognizable as vandalism. The most typical vandalism is delete the entire content of the page. Yeah? It seems like a fun thing to do for some people, right? They just delete everything, hit save, and now the page is gone, empty. But obviously, a robot will detect it and immediately revert it to the old version. But of course, this is part of the change history, so we always observe lots of deletes, right? So apparently somebody deleted everything, so, and then we say, this is an interesting pattern, but of course it's just vandalism. No, exactly. It's still part of the record. I guess there are a few instances where they will delete even the change history if there's illegal information on there and stuff like that. I think they remove that. But we don't see them. But in general, you see everything you do on Wikipedia, which is good, right? Some other data sets, so for DBLP, which we all know as researchers, we also have access to their change history, which is also quite a lot, right? And here, for instance, on the right-hand side, you can see which DBLP attributes changed the most, right? So, for instance, this here is the electronic edition, so the link to the paper that has the most frequent change. Not update, change. Not insert, but change, right? So people actually update this stuff. And you can imagine why, right? If ACM or IEEE change their link structure, everything has to follow up with it. So DBLP has to update all this stuff, right? Wikipedia I also mentioned, but we also not just look at info boxes, we also look at Wikipedia tables. So all tables you find on Wikipedia, quite a lot of data, 2 million different tables, which is also quite interesting to analyze. IMDb, we also have access to their changes, and you can see what's going on there. For instance, when people rate a movie on IMDb, that's a change record in the number of stars a movie has, for instance, right? Music data, etc. I'll show you an example from DBLP. This is a chart since 1999. This shows per day the number of changes that happened on that day. Okay? So it's quite spiky, right? So something must be going on there, right? And so we did a little bit of an analysis there and found, okay, what happened at that particular spike, right? And you can see which properties changed on that day, and the journals, the name of the journal changed a lot, right? 28,000 times the name of the journal changed. So we can actually then dig in and see, okay, what actually happened. You can see the old and the new, and you can see they changed the way they abbreviate journals, right, on DBLP. And that was on that one day, you know, a big change in particular on that one day. So it's kind of an exploration of, you know, the changes that are going on, which, you know, already is at least a little bit interesting. What you could do now, for instance, is say, okay, which journals did not change their name? And then you could, those might be data errors, so you go in there and say, okay, why did this journal not change its name on that day, right? And then you could say, well, you know, maybe it was missed, maybe there was a parsing error, maybe the name was originally misspelled. So this is why it's useful to also look at systematic change and find out what was going on and what was missed, maybe. Okay. So this is kind of how we gather our data, you know? Okay, so how do we model it? It's actually pretty simple. It's nothing super special. So we have all these sources of change, let's say different versions of a database and its log, transaction log, or deltas, or snapshots, or whatnot, and we put it all into a change cube. And the change cube has 4 dimensions, very, very simple, really. It's kind of like RDF data, where you have a subject, a predicate, and an object, and we just add a time dimension, right? So we say, when was the change, when did the change occur, to which entity did it occur, to which property did it occur, and what is the new value? And actually, most of the time, we don't really care about the value in most of our analysis, but of course, we keep it around just in case. Okay? So it's a very, very simple model, and of course, if you have when, what, where, and how, you want to ask why. That's why we're doing this research, because of course, we're not modeling the why. Yes? And we don't record the old value, but in essence, of course, we do, because we have the whole history. So also we do record, for us, the inserts. So when a new value appears, it's also a change from the empty value to the new value. So we can reconstruct, and I'll show you an example later on, we can reconstruct every table at every point in time. using the time, exactly. So if you want to know what the previous value was, you just look for the same property, the same entity, and the largest timestamp that is earlier than the current timestamp.
So why did you say this is not a temporary database?
Yeah, no, absolutely. It's, I mean, the way we model it is more like an, let's say, RDF, temporal RDF store, let's say. Absolutely. But the kind of analytics that we do is different, I would argue. Yeah, as I said, because we're not really looking at the values, we're looking at just the change itself, really. But I mean, yeah, it's not that far away. So just so you can see what this entails, right? So let's say you have an empty table, right? And then you insert one person. Those are two changes, right? Because we have a first name and a last name, right? Those are two change records, right? For person number one, right? Then we change the last name, and that's a change, right? Then we add another person, another two changes. Then we rename last name to family name, right? And those are suddenly four changes, right? Because family name did not exist before, so it was kind of empty from our point of view, right? So these are, in a sense, insertions to that attribute and deletions of the other attribute. So this is just an extremely basic way of recording it, but we argue that we can reconstruct everything from that model, basically. Okay, so what can we do with it? So I'll show you a short tool that we built to explore this data. So, as again, we have all our data, we transform it into the change cube, and then we have a visualization, I'll show you in a second, of this change data that allows you to filter it, to build views, to drill down into certain properties and certain entities. So this is kind of how the tool looks. I'll not show you a demo. If you're interested, ask Tobias later, right? So basically what you can see here is all the cities, right? And then for each, how many changes overall did we record for that city, and how many properties does it have, which were the top properties in terms of change, et cetera, right? And then you can drill down. You can click on any of those properties and say, okay, what about all the other entities that have this property? Can I reorder? Basically, I can just explore the amount of change that I can do, right? And one cool thing that Tobias built is a browser extension on top of Wikipedia. So this is a table in Wikipedia, and now our table looks like this. So you can take a slider and go to any point in time and see how did that particular table look in the past, which is kind of fun, right? So you can see, with this highlighting which values change the most, basically. Each of these dots is one version of that table. So that's why we also call it a new dimension. So here you just see one table, and now suddenly, in a sense, we're opening up the entire history of that table and how it came to be today. Right? And then you can kind of drill down and see what were the actual changes that happened on that particular day. Exactly. This is the idea, right? It's all pre-computed. Yeah. Exactly. Exactly. So, right? It is. Yeah. Exactly. Right. Yeah. So the queries that would be involved are quite complex. Absolutely. So this is pre-computed, but it's fun. I mean, it's really fun to see what happens. How do tables just come to be? So we're still in this kind of exploration, having fun with the data part. I'll come to some more serious applications. Yes. Yeah. This would be this tool. You can really look at everything from every angle, in a sense, right? You can filter, you can sort, you can group by, you can expand groups. It's really pretty cool to kind of explore what's going on, right? And you always see these. And that's a great interaction. You can limit the time frame, say, okay, what happened on that day, so you interact with that chart, etc. So it's really pretty cool. Again, this is really just to show there is interesting data out there to be had and to be looked at. Okay, so now one interesting difficulty, which actually turned into a research project of its own, is table matching. So if you have Wikipedia pages with different versions, and there's a bunch of tables on that page, right? How do you know what is the history of one particular table? right? This is what we're looking at. So here, I'll show you, I'll demonstrate this. So we have the complete edit history of a page and its table. So this is one table on that page from 2008. This is a table from 2010, table from 2017, etc. And you can already see the tables don't look exactly alike, right? It's not trivial. You can't just look at the schema and say, aha, that's the same schema. The schema changes, the organization changes, the sort order changes, a lot of stuff changes, right? And this table is nice. These are also kinds of tables that are difficult to parse. You just have to figure out kind of what's going on. You know, you have horizontal and vertical tables. You have a split web table. This is, you know, awful, of course. This is just one table, but taken partitioned into two and put next to each other. So I have to figure out. So if you insert a tuple over here, the last tuple will move up to the next line. So how do you recognize that kind of stuff? It's quite difficult, actually. You have to do a lot of parsing. Let me show you a particular example that makes it difficult. So this is about the city of Cape Town. And we have a table here. One table is about the climate, and the other table is about some sports teams in Cape Town. Okay. Then a year later, you have this sports table. The climate table is gone. It wasn't interesting anyway. Somebody deleted it, and it wasn't reinstated. Okay, fine. Then again, a little bit later, a few months later, suddenly you have three tables. So the climate table reappeared after a few months, right? And you have a sports table, and then there's a new one, a sports events table, right? And this is kind of how these pages evolve over time. So what we need to do is figure out that, you know, this table belongs to this table, these three are in one order, and this is a new table, right? This is, again, I can only emphasize, not trivial. Here's one example. This is the Chicago airports at 1 year, and then this is a new version of that table, right? And believe it or not, for 6 years in between, there was no table about Chicago airports, right? But there were thousands of versions of that page, right? So our matching task is to match this table into some version 6 years earlier of that page, right? So quite a challenging task, you know, scalability, but also, you know, I mean, the number of comparisons you have to do is crazy, and of course you have to be quite, let's say, relaxed to understand that this table is in essence the same as this other table, right? How many tables do we have per page? Let me actually go back. So you would think it's easy if I only have a few tables on a page, right? You'd think maybe on a typical page you only have one table or no table, right? But there are actually many tables, many pages on Wikipedia that have many tables, up to several thousand tables on a single Wikipedia page. This is, of course, an extreme case. You have many tables, for instance, for the Olympic Games, and then you have one huge page with all the results, etc., for instance, right? You can still see the majority has just one table, but you see, you know, some pages have many tables. So the first idea would be, let's match the table by order. The first table matches the first table, the second table, etc., from version to version, right? You would imagine the positions don't change that much, but unfortunately they do, right? So this again is one example for Chicago with manually annotated tables. They had up to 11 tables on that page. And you can see by their color coding that they do switch orders, new tables inserted at the top, etc. So if you just go by the order of the table and say the first table matches the first, the second, you're going to be wrong most of the time, or much of the time, right? So it's not as easy as that, right? Pages are much more dynamic. So what did we do? Well, we need to calculate some kind of a table similarity, and an obvious approach, which actually also works quite well, is using just a bag of words approach. So we don't worry too much about the columns, just columns and rows of the table. We just put in a bag of words and then calculate the similarity of the bag of words. Is that a question? Oh, I thought you were raising your hand. Sorry. No, okay, it's fine. Go ahead. Well, you can do better, but first of all, it has to be really fast, right? Because we have many candidates, right? And second, yeah. So. This was a quick and easy solution, and you'll see by the results it works very well. Tobias, interrupt me if I'm saying anything wrong. No. Okay. So we did think about lots of special things, right? We said, for instance, you could do schema matching and entity matching, and if they all nicely line up, then it's a good match. But this worked very well. So, I mean, in a sense, you could say, what a disappointment. We did not need a complicated solution. But on the other hand, you still have to build it and actually have to try it, right? Yeah. Yes. Yeah. Yes. Yes. Yeah. Yeah. Exactly. It's easy. One second. It's easy because we're always on the same page, and the changes from version to version are not huge, right? So the airport table was a problem. Yeah. Go ahead. Yeah, I get it. So I agree. So here, I think you're referring to the question. So you'd say, okay, name is name, that's fine. Airport code, is that this one or is it this one, right? So right now, the easy answer is we don't care. We just care. We just care about the fact that this table has changed, right, and can count the number of changes. But in essence, of course, you're absolutely right. Not only do we want to know what is what, we also want to know if, I don't know, this code here changed from that code right there, right? That's an interesting piece of information. This is also a kind of a current piece of work that we're trying to do. One thought is we look left and right, we look at this value, we look at the previous and the succeeding values, and see if its immediate neighboring context is similar, and then we could do a matching on a cell-by-cell level, right? Yeah. Yeah. That would be an application. That would be an application. Yeah. I can't offer you a solution. I agree. I agree. Okay. So here you can see this is just a nice visualization. Again, this is Chicago. All the versions, and then you can see for every pair their similarity, right? So you can basically say, so these are all versions of Chicago, the Chicago page. These are all versions of the Chicago page. And then we have a pairwise table similarity, and you can see that these similarities are high, which basically says that if they are close in time, they are also more similar, right? Of course, this version is not very similar to, that version up there because many, many years have passed. But if you're just looking on a day-by-day version, then the task is also a little bit easier. So that's how you can, that's why we're so successful. And you can see this on the right-hand side. You can see the results. So we're talking about, these kind of numbers. So this is F measure, 99%. So in essence, you could say it's an easy problem. But, so we also checked out some baselines, but, our approach just worked quite well. What you can see here is a visualization of each, or I think this is a subset of 1,000 tables, and how they change over time. So they all start up here, right? Some just stay the same, some change gradually, some change radically. So it's also kind of an interesting way to see how tables evolve over time, kind of, right? Okay. So this next slide answers your question. What we want to do, in essence, at some point next is do this cell-based matching. So again, it's not an easy problem. Let's imagine you have this table right here, right? And then you insert a tuple here. Everything else moves down one slot, basically. So it breaks all your previous matching, right? So the concept of a row ID does not exist in changing tables, for instance, right? So this is exactly the kind of problem we're going to be looking at next, right? So column matching, row matching, and then try to, can we see the change here? Up there is just a fun visualization of how tables change over time. So you can see there's actually a lot going on in Wikipedia. Okay, so what can we do productively other than have fun with this, right? So one project that we're currently pursuing is Schema Recommendation, right? So what we're trying to do is the following. We're looking at all tables of a certain schema, right? So let's ignore this. Look at this time slice here in 2009. These are lots of tables that have this schema that is coded in yellow, which is year, division, and position. This is about soccer, okay? So this is a table about in which Liga, which team scored in which position, this kind of thing, right? And so all these tables have that schema, and there are a few tables that have this, I don't know, beige schema, so it's slightly different. Actually, I can't even see what is the difference. Tobias, help me out here. It's just a different format. Okay, fine. So you can see this is a very popular schema, right? Many more and more tables have this particular schema. And suddenly, from one year to the next, it branched out. So suddenly, some of these guys stayed the same, but some of them turned into the blue schema, right? So they added the tier, right? It was this first league or second league or third league, right? And then even more branched out with some kind of a Bavarian specialty. I don't know, the Bavarian soccer seems to be different from everybody else's soccer, right? So you can see all the different kinds of schemas that evolved from this one original schema. And now the thinking is, can we recommend schema changes? So a recommendation could be, so let's say another schema, well, you could ask yourself, what about these tables here, right? Should they also use maybe the blue schema? Should they also use the orange schema? Because everybody else changed, they stayed the same. Can we turn a recommendation out of this? And of course, it's not enough to just look at the numbers. You have to look at the context, right? So we'd like to be able to recognize, okay, this is actually a Bavarian football league that this page is talking about. All the other Bavarian tables changed their schema, so we might want to change it as well. And changes might be adding an attribute, removing an attribute, renaming things. So these are all schema changes, right? And the thinking here is, our hope anyway, is over time, schemas become better, right? So Wikipedia is moving towards nice, consistent schemata. This is an assumption. I'm not sure if it's true, but if we take that as an assumption, we can say, look, if we observe certain changes over time, we might want to recommend similar changes, let's say to tables that are not updated that frequently, but that would improve their readability. So we've devised a way of modeling this. So we have, we're actually modeling this in a lattice. So here you can see a schema change. The right-hand side schema is team and W and D and L, and it was changed to spelling WDL out, right? Which is a nice change. I think that's a good schema change if you ask me anyway, right? And so what we do is we look at all subsets of that schema. So also we look at, for instance, team W and D. It's a subset of this schema, right? Because that's something that we might want to use as a recommendation. So if we observe this schema here somewhere in the wild, we might want to recommend, okay, this W could be wins and this D could be draws, right? So we don't only want to recommend something about this schema, we also want to make recommendations about sub-schemas, right? Which is why we build all possible subsets. And then each arrow is an actual change. And we can weight it by the number of times we have observed that change, right? And then we can basically make some recommendations, within this lattice or within this graph, right? So based on the observations we see, we can say, okay, here's a sub-schema that has evolved into something nicer. Let's recommend a similar change for other schemas. Also context-based, right? And we're working on this right now. These are preliminary results, but we're already doing quite a good job. So first of all, 95% of all changes do not experience a schema change in our validation data set. So we can't, so many tables don't change at all. And of course, if we want to recommend schema changes, we want to validate it by observing, did it actually change later on? And often, of course, Wikipedia is not that dynamic. Not everything changes all the time, right? So what we want to do is we want to evaluate this approach by saying, we recommend this change, and then we wait 1 year, and did it actually happen, right? Did a user actually do something to this table? And if it did, it's a success. If it didn't, we don't know. Maybe users were just too lazy to do something, right? But at least for those where the change was observed, we are actually quite successful. So this is the rank, which are, this did not work. I was just talking about fonts and different computers earlier, so even my own computer did not catch this font properly. But basically, this is showing that our recommendations are usually ranked very, very low. So it's usually the top or the second recommendation of change is something that then we observe actually happen, which is pretty cool. So we're recommending changes out of the blue and saying, and then suddenly we observe somebody actually changed it. And we're not, and I should say, we're not physically recommending it to anybody. We're just thinking this should happen. And apparently somebody on Wikipedia also thinks the same thing. Yeah? And we're very successful there. So this is kind of very promising to predict schema changes. And if we can predict it well, we can also recommend well. This is the idea. Okay, last project, and then we're done. This is about role matching. So this is kind of a new concept. This is also something that only comes up if you look at change data. So the thinking here is the following. If you look at the right-hand side, you will see the current US president, Joe Biden, right? And you will also see an info box about the armed forces, Army, Navy, Air Force, etc. And the commander-in-chief is the same person. So now if you go back in time on Wikipedia, you will recognize that also Trump was president and commander-in-chief. And you will recognize that Obama was president and commander-in-chief. And of course, that's not a coincidence. This is in the US Constitution. It says that the president is also the commander-in-chief. But Wikipedia doesn't know that, right? But we can observe it. So if we can observe that these two roles, commander-in-chief and president, always change at the same time to the same value, we can say there's an underlying match here, right? It's not a coincidence anymore because they always change in lockstep. That doesn't mean they change in the same millisecond, but maybe on the same day or within a week, there's always the change to the same value. And this is what we call a role matching. So the role of the president matches the role of the commander-in-chief. And this is something just by change observation, by nothing else. We didn't read the Constitution, we just observed these changes. Right? And so we built a system that actually analyzes all these changes. So what we do is we look at every value on every Wikipedia history and see how it changes, right? And then compare it with all other values and see if they change. Of course, you can filter this down and say, well, there has to be at least one value in common to start with, yeah? Hopefully more. We have to observe at least a few changes to make any kind of confident statement, right? So there's a whole slew of methods that you can try out, but in essence, what you're doing is you're looking at this temporal data, the changes. You need blocking methods, traditional for matching. So the blocking, as I said, is to say at least one value in common. And then you look at the actual sequence of changes and figure out, do they align well, right? And align well can be very broadly interpreted. Within a month, they also change. But life is a little bit more difficult because sometimes values are deleted or inserted. So sometimes there's no value at all for a certain period in time, but you still have to say, well, I think it's still a match. The value doesn't exist, but if it would exist, it's probably the same value, etc. Right? And it works pretty well. You don't have to read this data. We have 82% recall with some configuration, let's say, or some good parameterization. So that means that about 82% of all actual role matches we can find with this technique, just by looking at the data. So what I'll show you, actually, I'll skip this slide. I'll just show you some examples of what we found. So here, the chancellor of the University of Sahiwal, that I don't know, is also the chancellor of this other university in Iran. And there's an actual reason, right? So these are jointly appointed, but we recognize this through data, right? Here's another example, same situation as in the US, that Lula is not just commander of the Brazilian Air Force, but also of the Army. This is a fun role. So the role of the color of the right army, the right sleeve of a soccer team, right, matches the role of the color of the left arm of the soccer team, right? So basically, the fact that these match tells us that soccer teams always have the same color on the left and the right sleeve. It's fun at least, right? But we can use it for data cleaning, right? So if we see a violation of this matching, then we could raise an alarm and say, we think they should match, maybe you forgot to update that value, right? So there's all sorts of stuff in the data. This is the last example. So here, this is also an obvious one, but again, this helps in data cleaning, right? So these are British general elections, and of course, the prime minister after the election is the same as the prime minister before the next election, obviously, right? This is by definition, but of course, again, on Wikipedia, this data, nowhere this is encoded, right? Nobody's checking for this. These are just careful users making sure that this is gotten right. But we can now check for it because we know these are roles that should match, and now we can find all situations where they don't match and raise an alarm, right? This is the idea. I see some people nodding, so great. Brief outlook. One more little bit of fun that we observed. So systematic changes. If people go along and change lots of things, right? So this is, as you can clearly see, the state of Alabama and all its counties. And there's this one user called Hyperfast, a username of some Wikipedia editor, right? He updates the population of all these counties, right? Because there was a new census, and he does it for 66 out of the 67 Alabama counties. So this is a systematic change. He went along and changed everything except that one county. So now we could go along and say, oh, dear user Hyperfast, why did you not check that one county? Did it have no change? So it's an error, right? This guy went through every county and forgot one. Okay, fine. But we recognized it and could raise an alarm. But then interestingly, within 30 minutes, this other user, Altair's Far, right, reverts 61 of the changes by Hyperfast. So he says, wrong, 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 wrong. He reverts everything back for some reason, right? It's also a systematic change, but only 61 of the 66 changes, right? And then you can see a few weeks later, he reverts 4 more changes, right? But forgot still one change. So we have 2 errors here, right? One is Hyperfast forgot one state, and then Altair's Far forgot to revert one of these states. And again, we want to be able to recognize these changes and then basically, again, raise alarms saying this was a systematic change, but you seem to have forgotten something. Right? Maybe. Exactly. See, she said, you can have that one state. I'll revert everything except that one county. I'll give you that county. Right? I mean, whatever the reasons are, there's probably a good reason. Maybe the census was not correct or it was recanted. Who knows, right? But anyway, this is something you can do. And you can extend this, and this is something that we're going to be presenting actually at the next EDBT, is predicting changes, right? So we're analyzing the changes. So I talked about trajectories earlier, so we can see maybe regular changes. And so we can also predict and say, I expect this value to change next week. It's changed every week before, so it should change next week as well. And then if it doesn't change, we can raise an alarm. We can say something like this, say, that value seems out of date. It should have changed, or we think it should have changed, but it didn't change. Or the other way around, if there's an unexpected change, we can say, that was an early change, right? Why did this change? We didn't expect to change up, until next year, but it suddenly changed. Is it really correct? We can then double check with the user, let's say, right? So, and this works surprisingly well. We do this in a rule-based manner, so basically where we say, that gold scored changes, in certain months, once a week, let's say, or whenever a match was played, also gold score changed, and if it doesn't happen, then we can raise an alarm. So there's this kind of prediction that we can make, and as I said, this works quite well. And we can, on Wikipedia, what was the number? I think we can predict, 7% of all changes we predict correctly. This is amazing, right? So these are users fiddling around on Wikipedia, and in 7% we can predict it. And we don't predict anything for the others, so we're usually correct in our prediction. So we can predict lots of what's happening on Wikipedia. We can't predict the values, but you can predict there will be a change at that position soon. Right? And the last kind of future use case, which is really, really important, is vandalism. Right? So vandalism is also a change that we'd like to classify. It's a big problem of Wikipedia. And by the way, interestingly, if you guys are aware of Wikidata, vandalism is also a big problem on Wikidata, even though you'd think it's much more secluded, nobody knows about it, but there's lots of vandalism going on there as well. So here you see some fun examples of vandalism, but can we recognize these kind of changes, right? There's also vandalism in tables. So this is a fun example of Toronto, where you have the mayors of Toronto, and then they have the left office, the date they left office. And this guy, I don't know if you know Rob Ford, he was a drug addict and a crazy person, let's say. This is recorded. Well, I think he might have been a crazy person, and they said he left office inebriated, so drunk. But there's worse things. So this here is an awful example of somebody editing Wikipedia to prove a racial point. So this is the racial makeup of a certain community in the United States, and somebody edited it to increase the number of African Americans in that community. Maybe to say something like we're overrun by black people, or I don't know, some kind of a political statement by fiddling around in tables on Wikipedia. And this is something that we would predict, or we would predict there should be no change, and if there is a change, we should be able to raise an alarm and say, we don't think this is a correct value here, right? So this is actually an important topic. Okay, last slide. All of this is based on an original vision paper that we wrote, and I have here lots of challenges that we mentioned in this paper, and now looking forward to discussions and questions. All right. If there's time.
Thanks, Felix. Questions? One more question.
Of course. Yes. Yes. Which one?
So you said that you predict, right?
Yes. Yes.
Are you going to do it by sort of machine learning or?
This is rule-based, rule mining mostly, basically, right? At attribute level and at cell level. So at attribute level, we could say things like, whenever matches played changes, also goal score changes, wherever you are. That would be at attribute level, right? But also at cell level, right?
In order to do rule mine, you have to focus on the fragment of the data. So how do you choose the data that you look at? So you have in mind some rule and you ask.
No, I mean, you can just do association. Yeah, okay, but you can, no, we don't have to, I mean, we don't have a rule in mind.
If you have the Wikipedia, you
Yeah.
ask yourself, let's do rule mining.
Yes.
It's a nightmare.
Well, okay, but we have great students that overcome these nightmares and are good at implementing stuff. So it's not we don't have a rule in mind. It's, I mean, literally one part of this project was just association rule mining, right? A priori, or I think they used a priori actually, and just went through all change. So the table itself is quite simple, right? So it's not many attributes or so. So this is literal rule mining over everything with min confidence, min support. That's what we do. I mean, so the technology behind is more, as you also mentioned, about scalability, handling these large data sets, right? So, by saying the min support has to be at least something, but,
But then when you mine the changes, you just look at the single change. You don't look at the series of changes.
indeed, that would be room for improvement. Right, so the rules now that we get are not temporal rules in that respect. They are individual rules about attributes, let's say, right? They are not temporal rules, but there's another project that I didn't show here that also defines temporal rules. So that's saying if there's a change within this interval, there should be a change in this other place within a week or so. So we have a technique that does that as well. Yeah. So, but it is, yeah. I mean, yeah. What can I say? It's complicated, or it's not that complicated. It's cumbersome. It's a lot of engineering involved with these big data sets. Yeah. Yeah.
More questions? Yes.
Yeah, this is an overall vision, yes. Mm-hmm. So, well, first of all, this is real data. It's just public data, right? It's open data, okay, yeah. So it's a good question. So, I mean, I have to admit that this research has, so we all know as researchers it's difficult to get real world data, right? And I can tell you it's even worse to get real world data in many versions, right? Because they are often not kept around, right? So also transaction logs are not kept around, right? So all the data sets that I have shown you were kind of open, or we know the people and can ask them, but I mean, you can imagine the nightmare of clinical data. I mean, maybe you're working with this kind of data anyway, so that is a nightmare. But also, as I said, having then the history of that data is actually quite difficult. So what we have done, for instance, we've been to government websites and then crawled them every single day to then have 1 year worth of changes in the 100,000 tables that we crawled every single day, right? So this is still not real world data, it's government data that is still open, but it's more, let's say, tabular, more databasey than the Wikipedia stuff, right? But the same kind of principles, of course, also apply there. And maybe I didn't quite get your question right, but I kind of also understood that you might, so that we're doing too many things, let's say at the end user level, showing the problems, etc., right? And not so much maybe at the root cause of the data quality. So for Wikipedia, the answer is easy, right? Because the user is also the root cause, right? So Wikipedia changes by people looking at it and changing it, right? So it's a very closed loop here, right? But I agree, if you have let's say a data warehouse project or so, it's a different situation. But yeah, I don't have a good answer, to be honest, there. I don't think I do. Mm-hmm.
Okay, I have one question myself. In the old times of data quality, to in some way give more trust to a value with respect to another when you have contrasting values. Mm-hmm. You have either the so-called data steward or the methods to try to guarantee the trustfulness of the sources. Now, in one of your examples, the one on the changes in the Alabama counties, you have one change and then another one. So how can you establish which is the real value? I mean, do you have some hints, some approaches?
Mm-hmm. It's a good question. So well, we have thought about this. So for instance, if you have a user like Hyperfast who takes all the trouble of changing all the counties of Alabama, you and I would probably give a high trust to that person, right? Why else should he or she be doing that? Maybe, right? So I would say if there's a kind of a systematic change at that level, probably you'd have a higher trust than something else. So my answer in general is, how do we establish trust? How do we know what is the correct value? I think this kind of research does help you do it. So what you could do, for instance, with this thing, you could look at users who have done many changes that were not reverted. There's a bad example here, but there are many expert users who change a lot, and people agree and don't change it back or change something else, for instance, right? But also, as I said, if you have systematic changes, you could say, well, this is so systematic and people accept that this is a good way of doing it, this might be high trust. Or, as I said, we can mark, with this last project that I mentioned, if values are outdated, right? That's kind of a form of quality or trust. We say, look, this value hasn't changed in 5 years. All the other similar values have changed, but this one hasn't. So be careful, this might be outdated, right? So in a sense, we're saying the wisdom of the crowds, in this particular example, helps us assess quality of individual parts. But it's not the same as a real trust system, let's say. Okay.
More questions? Okay, thanks again.
Thank you.
There are newspapers in Italy systematically doing the change immigrants,
Oh, no.
similar
Yeah.
to the ones that we did for the black population,
Okay.
exactly with the same purpose.
Yeah, 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 yeah.
But this is systematic. So if you study the numbers,
Okay, okay.
names on newspapers, and then you see the
Okay,
changes,
yeah, yeah.
depending on
How far right they are.
the situation.
Okay,
Numbers are completely different.
okay. Yeah, very fun. Yeah, yeah, that's great. Okay, cool. Great.